Unit 1.3 practice problems. A 23.0 gram sample of a compound containing 12.0 grams of carbon, 3.0 grams of hydrogen, and 8.0 grams of oxygen. Which of the following is the empirical formula for the compound? So for empirical formulas, typically, if we're giving percent comps, we go percent to mass, mass to mole. We're going to then divide by small and multiply till whole. We've already got mass, so we can just go ahead and start there rather than converting to percent. So I can go ahead and divide each of these masses by the mass on the periodic table to give me the number of moles that it is. So 12 grams of carbon, the molar mass of carbon is 12, so 12 divided by 12 gives me 1 mole of carbon. Hydrogen, my mass is approximately 1, so 3 divided by 1 is going to give me 3, and then 8 divided by approximately 16 is going to give me 0.5. So I've done grams to moles. Now I need to divide by small. My smallest number is 0.5, so I'll divide all of these numbers by 0.5, effectively multiplying them by 2. So 2, 6, and 1. And then these are already whole numbers, so I don't need to multiply to a whole. I can just go ahead and identify that answer choice B is going to match the subscripts that I found. And so answer choice B is going to be my best answer choice. A compound containing 1.10 moles of potassium, 0.55 moles of tellurium, and 1.65 moles of oxygen. What is the simplest form of this compound? So again, we're asking for the empirical formula. According to my little rhyme scheme, I would do percent to mass, mass to mole, divide by small, multiply to a whole. I'm already halfway through this process. I have the number of moles, so I can go ahead and move on to the divide by small portion. So the smallest is going to be that 0.55, so 1.10 divided by 0.55 is going to give me 2. Anything divided by itself is going to give me 1. And this is going to give me 3. So my subscripts should be 2, 1, 3, and that is going to be answer choice C. A compound containing 30% sulfur and 70% fluorine by mass, the empirical formula of the compound is. So again, empirical formula, percent to mass first. So I'm going to go ahead and say this 30% is going to be the same as 30 grams, and 70% is the same as 70 grams of a 100 gram sample, and that's going to be the easiest way to get my mass. So percent to mass, done. Mass to mole. Now I'm going to divide each by the mass on the periodic table. Sulfur's mass is going to be 32 approximately, and fluorine is going to be 19 approximately. So 30 divided by 32 is going to get me slightly less than 1, so 0.9375, and 70 divided by 19 will give me 3.684210526. Divided by small is going to be the 0.9375. Anything divided by itself gives me 1. And then 3.68 divided by that 0.9375 is going to get me 3.9. This is going to be close enough to 4. And so we have the subscripts 1 and 4. And so that is going to be answer choice C. A compound containing 3.21 grams of sulfur and 11.4 grams of fluorine. Which of the following represents the empirical formula for the compound? Again, percent to mass, already done. So now I just need to go mass to mole. So we're dividing each by their masses on the periodic table. Same masses as last time, 32 and 19. So 3.21 divided by 32 is going to give me 0.1. 11.4 divided by 19 is going to give me 0.6. Dividing by the smallest number, that's 0.1. Anything divided by itself is going to give me 1. 0.6 divided by 0.1 is going to give me 6. So my subscripts are going to be 1 and 6 respectively. So that would be answer choice E. A sample of a compound that contains only the elements carbon, hydrogen, and nitrogen is completely burned in oxygen to produce 44.0 grams of carbon dioxide, 45.0 grams of water, and some amount of nitrogen dioxide. A possible empirical formula for the compound is... Okay, so with this problem, since we have just an unknown amount of nitrogen dioxide, we can't use the law of conservation of mass to help us at all. Instead, we're going to have to look at the overall proportion of carbon to hydrogen, and we can see that between all of the answer choices, none of the proportions for carbon to hydrogen match between the answer choices, so that's going to be our determining factor. We're not going to be able to determine the amount of nitrogen that should be present within the empirical formula at all. So we know that we have 1 carbon for every 1 carbon dioxide. So we need the molar mass of carbon dioxide. Carbon has a mass of 12, oxygen has a mass of 16. We have 2 of them, so that gives us 32, which means that our molar mass for carbon dioxide is going to be 44. So when we go from grams to moles, we're going to divide by the molar mass of carbon dioxide, which is 44, which gives me 1 mole of CO2, which is because of the number of carbons within CO2 is going to be the same. So I also have 1 mole of carbon. And then here we have 45 grams of water. We need the molar mass of water. Hydrogen is going to have a mass of approximately 1, and we have 2 of them. So 2 plus oxygen's mass of 16 gives me a mass of 18. So 45 divided by 18 is going to give me approximately 2.5. And this is moles of water, and I have 2 hydrogens per mole of water, so I need to multiply this by 2. Sorry, not the carbon. I need to multiply this by 2 to convert from moles of water to moles of just hydrogen, and so that gets me to 5. So I have the ratio 1 to 5. And the only answer choice that has that ratio is answer choice B. So that's going to be my answer choice. After completing an experiment to determine gravimetrically the percentage of water in a hydrate, a student reported the value as 38%. The correct value for the percentage of the water in the hydrate is 51%. Which of the following is most likely the explanation for the difference? So we did not account for enough water, and my mass should have been made up of more water than I actually calculated, which means I didn't get rid of all my water. So I'm looking for something along those lines, something that tells me I did not get rid of all my water. So a strong initial heating caused some of the hydrate sample to splatter out of the crucible. Now that would be a problem. It would, however, be a problem in the opposite direction. This would cause me to lose more mass than was appropriate. I had less mass lost than I should have. So answer choice A is wrong because it would have caused an error in the opposite direction. B says the dehydrated sample absorbed moisture after heating. This would cause my mass to artificially rehydrate and get too much water back inside of it. So I wouldn't have had it fully dehydrated. I wouldn't have removed enough water. So that's a good explanation. We'll see if any of them are any better. Option C says the amount of the hydrate sample used was too small. Again, not really causing the error that we're looking at here. Option D says the crucible was not heated to a constant mass before use. So this sounds plausible, But it's not the crucible that we're heating to a constant mass, it's the sample that we're heating to a constant mass. The crucible itself isn't absorbing a whole heck of a lot of water. Instead, it's a sample that's going to be causing my problem. So not the crucible being a constant mass, but my sample being a constant mass is going to be a problem. And then finally, excess heating caused the dehydrated sample to decompose. So again, this would cause more mass loss than was expected, not less. So that's the exact opposite problem that I had. Answer choice B is the only answer choice that matches, that we would have the correct error in the correct direction. And so answer choice B is going to be my best answer choice. Two different ionic compounds contain only copper and chlorine. Both compounds are powders, one white, one brown. An elemental analysis is performed on each powder. Which of the following questions about the compounds is most likely to be answered by the results of the analysis? So we're doing a elemental analysis to tell the difference between these two compounds. The things that I would be able to find out about that with an elemental analysis is what kind of compound I have, and so what my formula is. The density not really going to be given by elemental analysis. Formula unit, what is the formula unit? Remember, the formula unit is just my special term for a compound, a particle of an ionic compound. So you can, anytime you see formula unit, you can kind of think, hey, that's kind of the same thing as a molecule for ionic. Okay, so formula unit is the correct term instead of molecule, since they form large complexes. Instead of individual distinct molecules, but that could trip you up. So formula unit for the compound, that's a molecule for the compound. That's going to be my empirical formula. And that's going to tell me what exactly is the ratio between copper and chlorine there. So that sounds good. Chemical reactivity of the compound, not going to be determined by elemental analysis. And then which of the two compounds is more soluble in water? Again, not going to be determined by elemental analysis. So answer choice B is going to be my best answer choice. Complete combustion of a sample of a hydrocarbon in excess oxygen produces equimolar quantities for carbon dioxide and water. Which of the following could be the molecular formula for the compound? So for this specifically, we're going to care that on the other side here, we end up with the ratio of carbon dioxide and water being equimolar, which means that the coefficient in front of here are going to be the same. So let's go ahead and pretend like both of them are 1, okay? That means that my ratio of carbon to hydrogens is 1:2. There is 1 carbon for every 2 hydrogens. And so I need to find an empirical formula that contains this ratio. 2:2 is the same as 1:1, so no. 2:6 is the same as 1:3, so no. 4:8 is the same as 1:2, so looking good. And then the last one, 6:6, is the same as 1:1, so no. Answer choice C is the only one that gives me the ratio of carbon to hydrogen. That would be possible if I had equal amounts of carbon dioxide and water being produced from that combustion reaction. Which of the following compounds is the mass ratio of chromium to oxygen closest to 1.62 to 1? So we're gonna find the mass ratios between all of these answer choices. So chromium's mass on the periodic table is 52, and then oxygen's is 16. So 16 times 3 is going to give me a mass of 48. And so the mass ratio would be figured out by 52 divided by 48. I'm just gonna set these up for all of them before I move forward. But this is gonna be pretty close to 1. Next up, I have, again, 52, and then I just have 2 oxygens here, so that's gonna be 32, since 16 times 2 is 32. So 52 divided by 32. And then we have 52 divided by just 1 oxygen, so 16. Then we have 2 chromiums, so that's 104 divided by 1 oxygen, so 16. And then we have 2 chromiums, so 104 divided by 3 oxygens, which is going to be 48. So now I can go ahead and plug all of those into the calculator to see what my ratios are. So 52 divided by 48 is going to give me something a little bit more than 1, so 1.08. 52 divided by 32 is going to give me 1.625, so pretty close. 52 divided by 16 gives me 3.25. So that's way off. This isn't enough. So this is looking pretty good so far. 104 divided by 16 gives me 6.5, which is way too much. And then finally, we have 104 divided by 48, which gives me 2.17. which again is too much. So answer choice B is going to be the answer choice that has me closest to the ratio of 1.62 to 1. Not perfect, but it is closest. A student has 2 samples of sodium chloride, each one from a different source. Assume that the only potential contaminant in each sample is potassium chloride. A student runs an experiment to determine the percent by mass of chlorine in each sample. From the results of this experiment alone, which of the following questions is most likely to be answered? So we should know what the percent chlorine is based off of the mass of sodium chloride. And if we have a potential contaminant of potassium chloride, that would artificially increase the mass of the compound. And so if I run an experiment to find the percent chlorine in each of the compounds, in each of the samples, I'm going to be able to determine which one is closest to the correct percentage, which one should have the correct amount of chlorine present according to the mass. And so that is going to be the purity of the sample. Higher density, not going to help me with percent chlorine. Source of the contaminants, not helpful. And then which sample came from a salt mine, which came from the ocean, again, not helpful. My only option for a contaminant is potassium chloride. And so that's not going to help me differentiate between a salt mine and the ocean. There are lots of contaminants from both of those. The source of the contamination, again, not helpful. I don't know how to find that just based off of the percent chlorine present within the compound. And so just answer choice A, being the higher purity sample, is going to be the only question that I can really answer based off of the percent chlorine, which is going to just be a set percent for pure sodium chloride versus my samples that could be contaminated. What is the empirical formula for an oxide of chromium that is 48% oxygen by mass? So again, we have percent to mass, and so percentages add up to 100. So we have 52% chromium and 48% oxygen. So percent to mass, we're going to go ahead and turn those into grams and pretend like this is a 100 gram sample. Percent to mass, mass to mole, we're going to go ahead and divide each by their molar masses. So 52 divided by the mass of chromium, which is 52, which gives me 1. And then oxygen, 48 grams divided by oxygen's mass, which is 16. And then 48 divided by 16 gives me 3. So the ratio that I should see there is going to be 1 to 3, which is going to be answer choice C. What number of moles of diatomic oxygen is needed to produce 14.2 grams of tetraphosphorus decoxide from phosphorus, where we have the molecular weight of the phosphorus complex as 284. I have a couple of options for how to solve this problem, but I'm going to solve it stoichiometrically. And so I'm going to go ahead and state that I'm looking for moles of oxygen when I have 14.2 grams of P4O10. I do need the reaction, so phosphorus plus oxygen going to that P4O10. Then I need to go ahead and balance, and that's that compound or complex balanced or reaction balance. Going from grams, I have the molar mass of the phosphorus compound already given, so I'm going to go ahead and steal that. And then moles of the tetraphosphorus to oxygen, I have for every 1 mole of P4O10, I have 5 moles of oxygen. And so then I just need to go ahead and plug that into the calculator. And I end up with 0.25 as my answer. This has 3 sig figs, so I'm going to go ahead and tack on an extra 0 at the end there to give me to the correct number of sig figs, and that matches answer choice D, so that's going to be my answer choice. A student has samples of 2 pure compounds, X chlorate and Z chlorate, which contain unknown alkali metals, Z and X. The student measures the mass of each sample and then strongly heats the samples to drive off all of the oxygen, leaving solid residues of XCl and ZCl. The student measures the mass of the solid residue from each sample. Which of the following questions can be answered from the results of the experiment? So since they're both alkali metals, our percent chlorine, or sorry, our molar ratio of chlorine is going to be the same here. We have 1:1 for both compounds. And if we drive off all of the oxygen, we are just going to be able to figure out which compound weighs more for a given number of moles of that sample, since we'll know how much is chlorine. And so the boiling point is not going to be able to be determined. Melting point also not answered by driving off the oxygen, and then density also not answered by this question. So answer choice A, the greater molar mass, is the only question that I could reasonably answer out of these 4 options there. M plus is an unknown metal cation with a +1 charge. A student dissolves the chloride of an unknown metal, MCl, in enough water to make a 100 milliliter solution. The student then mixes the solution with excess silver nitrate solution, causing silver chloride to precipitate. The student collects the precipitate by filtration, dries it, and then records the data as shown below. The molar mass of silver chloride is 143 grams per mole. So the mass of the unknown chloride was 0.74 grams. Mass of my filter paper was 0.80 grams, and then the mass of the filter paper plus the silver chloride precipitate was 2.23 grams. And then I am asking, what is the identity of that unknown metal that formed my metal chloride? Okay, so first up, I'm going to go ahead and find out what the actual mass of the silver chloride was. This is the filter paper plus the silver chloride, so I'm going to go ahead and subtract them out from the filter paper. So 0.8 subtracted out is going to give me a mass of 1.43 grams. Then I can find the number of moles of silver chloride that was present, and so I'll have the 1.43 divided by my molar mass of silver chloride, which was given as 143 grams per mole, and that means that I am dealing with a grand total of 0.01 moles of silver chloride, which means that is also going to be the number of moles of my mystery metal chloride compound as well. And if I go ahead and divide my initial sample's mass of 0.74 grams divided by my total number of moles that was represented within that mass of 0.01, I will get my molar mass of my mystery compound. And whenever I plug that into the calculator, that gives me a molar mass of approximately 74 grams per mole for my mystery metal compound. So now I just need to go ahead and find the molar masses of all of my options here and see if they are reasonable. So sodium has a mass of approximately 23 and chlorine's mass is approximately 35. So that would give me a mass of 58, not close enough. Potassium has a mass of approximately 39. Again, we have a mass of approximately 35 for chlorine, which gets me to 74. So that's looking pretty darn good there. But we're gonna go ahead and check the rest. For copper, we have a mass of approximately 64, chlorine again at 35. So that would get us to a mass of 99. That's too much. And then lithium chloride, we have a mass of approximately 7 for lithium and 35 for chlorine. So that would get us to 42, which is not enough. So answer choice B is going to be the only answer choice that gets me to a molar mass that is, well, actually it ended up being exactly, but close, anywhere close to the mass of that mystery compound that we found earlier. To determine the percentage of water in a hydrated salt, a student heated 1.2346 grams of that sample salt for 30 minutes. When cooled to room temperature, the sample weighed 1.1857 grams. After the sample was heated for an additional 10 minutes and then cooled again to room temperature, the sample weighed 1.1632 grams. Which of the following should the student do next? Now, we are trying to get rid of all of the water, and that means that our overall masses need to be the same after multiple heatings so that we can prove that we did in fact get rid of all of the water. Since we have a decrease in mass after we heated it again, we didn't have a repeat in mass, which means that we lost more mass between heatings 1 and 2. And so that means we are not done heating. So we're gonna go ahead and look to see if we have an answer choice that says, keep going, you're not done. Answer choice A says, use the smallest mass value to calculate the percent water of the hydrated salt. We have no idea if this is going to be the final mass, because we haven't had any amount of consistency yet. So we can't just go ahead and assume that we're done. So answer choice A is not going to be a good choice. Answer choice B says, repeat the experiment with a brand new sample of the same mass and average the results. So again, we have not proved that we are done getting rid of all of the water. Just repeating the experiment is not going to help me. Answer choice C says, repeat the experiment with a new sample that has a different mass. Again, not going to help me to prove that I was done heating up the sample to get rid of all of the water. Answer choice D says, reheat the sample until the mass is constant. That one sounds like the answer that I predicted, where we are not quite done with our experiment yet. Then answer choice E says, use the average of the masses obtained after 2 heatings to calculate the percent water. Nobody do da. Again, we are not done. We haven't reached a consistent mass level. We have no idea if we still have more water in that compound or not. And so we are not done, and we need to keep heating up that sample until we no longer have a change in our mass to be able to calculate the percentage of water that was in the initial sample.